Okay, so before we get on to improving the Broyden method, what I want to do first is one, test the method we have, and two, add a constraint. Sounds relatively simple, but run into a thing here or there. So a good test function is the Rosenbrock function, because finding the absolute global minimum is very difficult since there's a long part of almost connected, and things with round off errors can have difficulty. So let's implement it. So we're going to define the Rosen function. And trust me here, it's basically exactly what the Wikipedia article says. But it's 100 times x1 minus x naught squared, quantity squared, plus 1 minus x naught squared. Cool. And then we have to define some constraint. And we have to remember that this constraint is something equals 0. So in this case, for example, if we want 2 times x naught plus x1 equals 1, let's say. Oh, space though. Then we'd have to do minus 1, so that'd be equal 0. Now, what is actually being solved for here, for the Rosenbrock function, is the gradient of it, right? So what we're going to want to do is going to define the grads of everything, x turn it, yeah, jax dot gradient of the Rosenbrock function for x up till 2 and I'll come back to that up till 2 later. And then x to 2 times gradient once again, jax dot gradient of the constraint of x cool beans up till 2 once again, and then x of 2. And essentially what this 2 is, it's called a slack variable, which helps avoid round off errors when dealing with something like gradient. If you have a really small number minus a really small number over a really small number, you can get wild results. And so the fun little tool here, jax.jit, is something that just goes to the GPU and makes things faster if it's available on your computer, because defining the equations that we're going to use in the end can be a little expensive. So return JNP concatenate, and we can look up what that does. Effectively np.concatenate. And what it says it does is it joins a sequence of arrays along an existing axis. So what we are doing is combining the gradient up until 2 with that the whole 0 and 1 being the actual things we're looking at, and then adding on something called JMP at least 1D in order to avoid errors of the constraint of X, essentially just so that in the end the number we get for the third value is what the constraint value, like it should, the solving for 0 of the constraint value. So make sure this works. Cool beans, defined all that. And now let's define an x naught. Let's make it JMP array. Instead of all zeros, we're gonna do 0, 0, 1, because all zeros would not satisfy the constraint that I made up. And then let's do it. Broyden of the equations and our initial x's. Houston, we got a problem. Expected callable value got gone. This is interesting. Let's see. I have, it's likely just a typo here. I got all my colons. We're defining equations, EQS, EQS. It's not x1, up until 2, 2 times Jack's grad. Oh, that's where the typo is. Watch the parentheses, kids. Okay. Even if there's an error, sometimes there's an error. Okay, so these things aren't particularly close to 0, but I can tell you that within the constraints that we have, that's the closest to 0 we could get of all the values equally considered. And so with the power of jack shit and things, even this simple Broyden method isn't that bad with constraints.